Yes, it looks great. So our last speaker of the day is Milad from Columbia University. So take it away.
Thank you so much. So as the title suggests, I'm talking about some concentration inequalities for heavy thread distributions. This is a joint work with Professor Maleki and Professor De La Pena. Let me start with a motivation. So in inverse problems, we are interested in recovering a signal x from its measurements y1 to yn. And in the measurements, some sensing vectors are involved, AI, which are sometimes random. And it's quite usual to define a cost function like this and minimize this cost function to estimate for signal x. And to solve this optimization problem, the stochastic gradient descent is a common method where we start from a good initial point in x0, and at each step we move toward the negative direction of the gradient. So note that the function f, the loss function, is random because the randomness involved in the AI. And so the gradient would be random, and as the sample size grows to infinity, the gradient concentrates around its expectation, and hence the deviation of this random quantity becomes an important quantity for our analysis of such algorithms. Actually, because of the additive form of this loss function, the gradient would be additive, and if we assume AI are IID random vectors, this is going to be sum of IID random vectors. And hence, we are interested in the probability of deviation of such sum from its expectation. It's important to characterize the convergence rate of a stochastic gradient descent and its sample complexity. So to formulate the problem formally, we have Zi, IID random variables. We are interested in the probability of deviation of the sum from its expectation. And we want to upper bound it in terms of the deviation bound epsilon and the sample size n. By the law of large number, we know this upper bound goes to 0. The question is how fast this convergence happens. And we can ask this question when epsilon is fixed, or when epsilon is a function of n, which vanishes as n goes to infinity. We are not interested in any upper bound. We are looking for sharp one. And in order to assess the sharpness of our bound, we consider a lower bound for the same probability and say the bound is sharp if the limit of upper bound to the lower bound goes to 1 as sample size goes to infinity. You might notice that I motivated the problem for vectors, but stated for scalars. It's easy to see with a projection and epsilon net argument, one can extend the scalar result to the higher dimension. So no generality is lost here. And it turns out the tail of individual summands plays a key role in the concentration inequality that we are looking for. And in fact, very good inequalities are known for two classes of random variables. The first one is subGaussian random variables, for which the log of tail behave like a quadratic function in T, or something larger than that. Normal distributions, Bernoulli distribution, or any bounded distribution belong to this class, for which there is a general Hoeffding inequality, and says you can take the upper bound in the following form: exponential function whose exponent is quadratic in epsilon and linear in n. And of course, for sending this upper bound to 0, one needs to take the well-known square root n regime for epsilon. The same story happens for subexponential random variables whose log tail is like a linear function. Chi-square distribution and exponential distribution are examples of this class, for which there is a Bernstein inequality. So due to Bernstein, we can have the upper bound as a worst case of these two terms. The first term is exactly what we had for the subGaussian class, and the other one is something similar to the tail of individual summands in our sum. What I want to point out is in inequality, we see two regions. For small epsilons, we see a Gaussian behavior, and this is actually because of central limit theorem. This is going to be eventually Gaussian, but for large deviations, we see something similar to the individual tail of our summands. In the interest of time, I just skip the proof of these well-known inequalities, but let me just point out, for rest of the talk, I assume our random variables are centered. Shifting does not change anything in this problem, and that the moment generating function plays a key role in the proof of inequalities I just talked about. In order to present our results, I need to define the rate function as the negative log of the tail. And with this definition, subGaussian class corresponds to the quadratic rate function, subexponential corresponds to linear rate function. And as soon as the rate function gets sublinear, we are in the case of heavy tail distribution. It's easy to get a heavy tail random variable simply by multiplication. In particular, if you raise a normal random variable to any power greater than 2, you get a heavy tail random variable. And here is what happens for the moment generating function. For the subGaussian class, moment generating function exists anywhere. For the subexponential class, it is finite in the compact interval, including the origin. And as soon as we get into the class of heavy tail distribution, moment generating function does not exist anywhere. And hence, it's not trivial how we can extend the previous results for heavy tail distribution. Of course, there have been other works studying heavy tail distribution and proposing concentration inequalities, but in the interest of time, I don't go to the details of these works. Let me just recall the definition of rate function as the following. I also define a function I captures the right tail of a random variable if the following inequality holds. The whole point of this definition is we don't need to work with the exact value of the rate function. A lower bound for it is enough for our inequality. And here is the simplified version of the inequality we proved in our recent paper. So similar to the subexponential class, we proved there are two regions for large deviations when the epsilon is larger than some specific amount epsilon 0. We have a tail which is characterized by the tail capturing function as the following. And for small epsilons, we see something similar to the Gaussian. So in this display, C and beta appear here are eventually tend to 1. They are bounded constant between 0 and 1. And for now, you can assume these two are 1 when n is really large. The constant that I want to talk about more is this one in the denominator. And basically, this concentration inequality is applicable whenever we can bound these C and epsilon and beta, which I talk about it more in this slide. So CL and beta is defined as the following. The superscript L denotes the truncated version of random variable Z, and CL and beta is the following expectation. If you ignore this exponential term, is nothing but the variance. And in fact, we proved in our paper, whenever the variance is finite, we are able to upper bound this quantity and hence apply our concentration inequality. So we also showed this concentration inequality is sharp. Let's say we fix epsilon and send the sample size to infinity. In the first region, for the large deviations, for two general classes of rate functions, we have shown this limit is going to 1 as sample size grows. So the first class is when IT is alpha root of t corresponding to the subWeibull random variable. The second class is those with logarithmic rate function, which have, in fact, polynomial tail as the random variable. Also, in the Gaussian region, if I rescale the problems to put it in a familiar form, we get the following as the upper bound, and this constant that we talked about eventually converges to the variance of random variable. And basically, this is the same bound we can get. These have the same order we can get for the limiting distribution of the left-hand side. So again, in the second region, we can have this limit is 1, and hence the concentration inequality is sharp. While I just state this for fixed epsilon, we could consider some dependency of epsilon to the n, and we discussed this in more detail in our paper. In those regimes, this concentration inequality is sharp as well. So in the interest of time, I skipped the proof sketch. Let me just conclude that we developed concentration inequalities, which work whenever we are in the attraction domain of normal distribution. They are ready to use inequalities. One just need to bound the expectation of a smooth function in the definition of CL and beta to use them. We shortly characterize two regions, the subGaussian region and the region of large deviations. And we have shown the inequalities are asymptotically sharp. And these inequalities are applicable in many machine learning problems and data science analysis, similar to one that I just discussed at the beginning. That's it. Thank you. Thank you for your time.